So in proof number 6, which we've explained earlier on the website, I will just briefly go over the basic attributes of what we mean by squaring the sides of a Kepler golden ratio right triangle. I try to get all of this on here for you, and we will look at the various portions of it. The thing that we do in this one that's different than proofs 1, 2, and 4, which you probably just saw, is that we just jump right to the Kepler triangle. There's no need to draw the golden ratio geometrically and then get the Kepler triangle. In fact, this Kepler triangle here, sides 1, square root of phi, and phi, it was taken from proof 4. It's the same sides, it's the same Kepler triangle. And there are some special attributes of the sides of Kepler's triangle. What is meant by squaring each side of Kepler's triangle to the next larger side is if you take the hypotenuse, which is phi, and you extend the diameter out to here, you can, and just pick the center point and draw that circle, the green circle, with the diameter equals to phi. If you take this side, square root of phi, and just put the center here and draw a square, okay, centered on the circle, the square side will be the square root of phi. So you have a diameter of phi for this, and you have a side of square root of phi for that. The thing that we want to show is the perimeter has nothing but constants. It's 4 times the square root of phi. So the perimeter is 5.0880 and on out further if you wanted to use more than the measured value of that we did physically, the measurement of circumference equal to pi with a tape measure, and we cut the circle. The circumference would equal 3.1446, that's what we measured, and so out to 4 decimal places we see the circumference is also equal to 5.0880. So that's 4 decimal places. We can carry this out to as far as we want for the perimeter, and what we wanted to do was we could have just as easily inserted use 9 digits of pi, since we know it's more than this from previous proofs. We could use 20 digits, we could use how many ever digits you want and carry it out here. And what we're discovering is that we're just really refining the precision of pi out to these decimal places. And when we equate the circumference at first, even the 4 digits to the 4 digits, we equate them. We have the equation pi times c equals 4 times b, or pi times phi equals 4 times the square root of phi. The only variable left in this equation, since circumference equals perimeter, is pi, and that equals 4 divided by the square root of phi. It's true for this level, and it's true for 9 digits, it's true for 20 digits, 30 digits, and so we went ahead and we multiplied 40 digits of pi from the equation times 40 digits of phi. So we end up with, here we're showing 30 of them, all the circumference size out to 30 decimal places. And lo and behold, it equals exactly the perimeter of the square. So the green circle circumference equals the perimeter of the red square. No matter what size value of pi you use, and you correlate it to, wherever the value is on here, 20 decimals, 30 decimals, this is what it equals. That's what I call case 1. We can do the same thing down here for, let's bring this down a little, what I call case 2. You do the same thing, pi times this side equals 4 times that side. And you can go through the equation here. I don't care if you use 4 digits that we physically measured or you want to use 9 digits that we've calculated. Take your pick. Out the 4 digits, we see that it's 4 times 1 is 4. And we also see that pi times the square root of phi also equals 4. So Once again, when circumference equals perimeter, we can solve for pi, and pi equals 4 over the square root of phi. This is case 2. You can see the square, purple square, is one unit each, and this circle is also equal to the perimeter of the square. It's 4. Moving over to the third case, pi times this side equals 4 times, this a little bit different, 4 times side A divided by side B, and that also equals 4 times side B divided by side C. It's the same. It's just, once again, it's a special golden ratio right triangle, and you can go through the same computations here, carried out to the known measured 4 decimal places, although we've computed out to more. And since circumference equals perimeter, we can solve for the equation, and in both cases, because there are 2 cases here, 2 portions of a case here, pi, when you do this calculation, pi will equal 4 over the square root of phi. So in this case, it happens to be pi itself, because we chose a unit of 1. What we're really showing here is that, and through refinement of the previous proofs that we've done, geometric proofs, is that pi is a phi-based phenomenon. Not only that, but if you upscale the Kepler triangle, that is, multiply each side times a number like 7 times each side, it's the same as if you did 10 times each side or 1,000,000,000,000 times each side, except that my case 3, that is not true then. It will not be true as these sides are still true. Well, that's the same thing as Kepler's discovery about the golden ratio right triangle, where he discovered A times C equals B squared. That might be true for Kepler's triangle, but it's not true for a 1 square root of 2 or 3 4 5 regular right triangle. Kepler's discovery is not true. Moving back 1, so we move from mine, where part of it's not true if you vary from the golden ratio. And if Kepler varied from the golden ratio, his discovery is not true. And if you go back to the original golden ratio of 1.618033989 and its reciprocal, no other numbers fit that. Only that number fits it. That's why it's called the golden ratio. So we see an interesting phenomenon here, and the main thing that we've noticed is that pi is just one of many universal constants. If you put all the physical attributes of a squared circle, the circumference I'm talking about, and lay them out in a chart, you'll find out that there are many other universal constants, and they all contain either phi, a variation of phi, or the square root of phi. So the phenomenon of pi really is a phenomenon of the golden ratio phi. You can look at you can look at the Excel spreadsheet on my website and see for yourself. I'm sure you can come up with some universal constants yourself. So good luck.